Okay, so mind if I start up here? So we're wondering what the K constant is and what two equations it appears in. So, yep, it's a spring constant. That's another name for it. And these are both the same equation, just rearranged. The relationship between force and stretch. Yeah. So yeah, there's still the one. Wait, not K to the power of X. Yay, here we go. Here's the two equations. So here's the one. This top one is Hooke's law. So it's the force you apply to that spring is proportional to how much it stretches, and that is based on the K constant, which is how stretchy the spring is, basically. And then here is the potential energy of a spring. So the K here is the same K as that, and this X is still the same X as that. Which, remember, the X part of it is the difference between how long the spring is normally and how long it is when it's stretched out. So it's like a really delta X, but it's not too easy to type in the delta symbol. Is it all coming flooding back? Okay. Well, so today's topic is basically a chapter, like the whole entire chapter in one day. Yeah. So this is, and then we're gonna do a quick little like CER type lab. So here's your title for today, and these will be all the notes for Unit 6. Simple harmonic motion. And this was supposed to be an animation. I'm really mad that it's not animating. Okay, are all of my animations like this? Okay, never mind. So just this animation is musted.
At 6:30. Okay, I'm not waiting until next month.
Yes. Okay, so see the two stacks of blue books? In between those, there's several different cups of pens and pencils. So those are all up for grabs. All right, so we got all our notes all dug out. Yeehaw. Okay, so simple harmonic motion is basically uh, a special type of motion where basically something happens in a cycle. Yeah, so much moves. And so a lot of times you'll see simple harmonic motion abbreviated as SHM because that's just a lot of words. Oh, yeah. No, I'm telling you, like, it's literally just one day's worth of notes for the whole chapter. Yep. No, I would say not very. That's the spirit. Oscillation is something where it's going back and forth. I guess I need a spring and a thing.
I was just gonna wait until you come there and get it. Stop this. I went there spring break. No, because my VOE changed. So I had
If you want, but you don't really have to.
It would make sense to me.
Yeah, I'm a picture person.
Yeah.
Yes, and you have to make the drawing on your page move also. Oh gosh. Okay.
No.
All right. So, this definition here is saying that simple harmonic motion is a periodic motion. So, what is in physics? What does period mean? And it's symbolized by T. Yeah. So yeah, The only sense that we've seen period in this class so far is for an orbit. So, like, what's the period of Earth's revolution? Or no, rotation. Sorry. 24 hours. Yeah, and like, what's the period of its revolution around the sun? Yeah, 365 days or a year. So those are periods. But basically, eventually the Earth will come back to the same basic place it was before, even though technically it's not the same in 3D space because we're also hurtling through space, revolving around a black hole. But that's, yeah, don't think about that. But basically, so yeah, it takes a certain amount of time to do one cycle. So for this chapter, we're more so going to be talking about weights on springs. So like if I take this spring and this weight here and I let it bounce up and down like this, eventually it'll come back to the place it was, and that will be one cycle like that. So that's a periodic motion or an oscillation. And then also we'll do pendulums. So pendulums are just things that go back and forth, like so. Ooh. And basically it will come back to this point, and that's a whole oscillation. Exciting?
No.
No.
No, sorry, not you.
Oh, fair. Okay. So the next slide is kind of righty, but it's like basically all of the vocabulary on one page. So don't freak out. Okay. So oscillations, you can plot them as a wave. And you may have seen that wave in math class. Math class. Hey, this school isn't that rural. Yeah, I know. This is the part of physics that lines up exactly with pre-cal. And I'm sorry.
Oh no.
I answered a spam call yesterday, and today I've gotten 8 spam calls. So exciting. Yeah.
I just don't answer my phone. Which I found it really bad because apparently Scarlet Bear has been trying to call me for the last month or so.
Oh no.
Because my name is still in my system from signing up to do an interview.
Mm.
I did an interview. And I got a job there and it didn't show up because I had a job at Olive Garden because I had forgot to just tell them. Wasn't
Well,
working for them.
bless their hearts.
I care. Still care. No. Yeah, I did. Is the oscillator the thing that's doing
Yes. Yeah, the oscillator is basically like the subject of your sentence.
Yeah. No, it's not. I could lay eggs. What?
Shut up.
I'm sorry, that was not allowed. I don't. I kind of.
It's okay. You don't gotta explain it.
You might have to carry them to church. Give them birds some eggs. Give them let them.
Then you could just put it in an incubator and not have to deal with everything else.
I think that would be great. Oh,
Yeah, and then they just hatch. I dig it.
Sit on it.
I think that's the next step. Is not old man.
Right, like, because, yeah, the other option sounds horrible.
But also, it could backfire because there's like that bird that its entire body is.
Oh, the kiwi. Yeah, that's pretty horrifying, too.
That could be us.
Uh, yeah, and I guess the whole entire same size animal comes out of the egg as the egg itself. Yeah, okay, maybe it's really not that good.
You don't know? It tells you the film.
I think we should just release spores. Like, you just go stand in the wind. Yeah. Yeah, let's just be plants.
I think mine says in the paper.
There wouldn't be any global warming.
You can take them. Because you gotta hold it. You gotta hold it for 6 months.
Okay.
This is an interesting philosophical discussion.
Maybe you can take it. I don't know if you guys signed up for it or you just gotta do it.
So, is everybody basically done writing the vocabulary so I can talk about it?
Yeah.
And maybe get us off of the subject? Okay, so an oscillation, remember, is just basically, I'm just going to keep using this pendulum because it's easier than the spring one because it keeps falling apart in my hand. So, like, one oscillation is just like one down and back, like that. So that's one cycle. Which is an oscillation. So just one complete motion all the way there and back. So that could be like one rotation around the sun, or it could be one up and down with a spring. The period is how long it takes to do that. So we already have these two little equations in your notes, but hopefully you just rewrote them again. So the period is equal to 1 over the frequency. So the frequency is basically how many things you do per second. So I guess I can't really do that one very fast. Let's see. Can I do this one faster? No. So yeah, pretend it's like jumping up and down and up and down. So however many of those I can do in 1 second, that's my frequency. And frequency and period, if you'll notice, the equations are exactly the opposite. So they are, oh my gosh, inverses. There we go. I was going to say proportional. Like, no, the other word. They are inverses of each other. Period is just measured in seconds, and frequency is measured in hertz, which is just 1 over seconds. It's also named after a guy. The amplitude is how big your displacement is, basically. So I could do a low amplitude swing like this, or I could do a high amplitude swing like that. Exciting? And so the higher your amplitude, usually the more energy is going back and forth. So it would take less energy for me to bring the oscillator from here to here than it would from here to here. And then the equilibrium is basically from the middle point here. So like if my pendulum is just resting, then this is its equilibrium position. And if I take it over here, now it's out of equilibrium, and that's why it will swing back and forth. And eventually it will come to rest at its equilibrium point. So the same thing with the spring. Oh, no. And don't tell anyone about that. So I have a plan for that. So like if I don't have this mass bobbing up and down at all, this is its equilibrium position. And if we were talking about Hooke's law, then the distance would be the difference between this position and when there's no weight on the spring at all. And when it's bobbing, its equilibrium position, hold on. So its equilibrium position is about right here. Here, let me line it up with the table. Now watch how it goes both above and below the table. It's really not very exciting, huh? This one's not very stretchy compared to the other ones. So your equilibrium position is in the middle, and it will bob up and down above and below the equilibrium position. So like imagine the water in a pool, and it's, just perfectly flat. And if you jump in the pool, the water level will go above and below that. So that's what we're doing. Yeah, waves. So you may have seen this in math class, or you may be seeing this type of deal. More animations. I know. This is when I figured out how to put GIFs in here last year. But now I kind of wish I could just pause it. Can I? Nope. So the unit circle whole thing is talking about this. So the radius is over here. See how there's a blue dot and a red dot? And the blue dot is just going back and forth on the x-axis. And the red dot is just going back and forth on the y-axis. See that so far? And so when your radius is going around, it's making a right triangle with bigger and smaller sides based on where it's at in the circle. And if you were to plot that over time, then you get the sine and cosine waves. Ooh. Wow. Are you guys all having to memorize the angles and stuff right now? If you're taking pre-cal. So yeah, don't worry. We don't have to do that much of that. We're mainly just going to be dealing with springs and pendulums for this chapter. So for springs, you may want to just write these equations down on this page so you have them, but they should already be in your notebook somewhere. Yeah, so these are our equations that we know about springs so far. Oh, I didn't realize I made my text so big that the equation went over. I'm sorry. So this equation here should be all in one line. I'm sorry. So it's 1/2 kx squared. I didn't realize I made my text too big.
It's not even a test, it's just a regular driving course.
I did the parent-taught driving course, so I didn't actually have to take a driver's test. I still can't parallel park. See, an hour and a half is probably how long it would take me to parallel park a car. I've only successfully done it once. Usually just avoid doing it. Or Chinese fire drill with whoever's riding passenger.
What?
Like when you stop at a stoplight and you switch chairs with the passenger.
Oh.
Chinese fire drill. I don't know why it's called that. Probably. Good point. Okay, so we got our two equations, and we noticed that I messed up the font on the second one, so it went on 2 lines. So far we just know K and we know X. And just remember, I'm going to keep reminding you guys that X is the difference in distance between when it's like this and when it's like this. Because I had a lot of y'all in the energy unit try and tell me that like this whole length was X, but that no. Mm-mm. Okay, so we have a new equation for a spring. You ready? The period of a spring. Woohoo! So the period of a spring is how long it takes for it to do one cycle like this, measured in seconds. And this was supposed to be an animation, and I'm really mad that it's not going. You just can't have nice things.
What?
This is supposed to be an animation.
Oh, should we write this down?
Yes, this is the new equation. Oh, I forgot to turn on my mouse sparkles. Hold on. Yeah, it's a new Chrome extension. It's really slow. Yeah, see? Now it's not letting me turn on my mouse sparkles. It's like a Chrome extension that makes my mouse sparkly. How about this one? Oh, it only works on that window? Anyway, so you'll see here is, remember that the letter T stands for period because it's like a period of time. And this is measured in seconds. Then we have a 2 pi. Why do you think there's a 2 pi out here? Yeah, that's the whole unit circle. So 2 pi is how many radians are in a circle. So that's a full circle. And then M, what does M stand for probably? Mass. What do we measure mass in? Kilograms, yeah. And then here we have K, and that's our spring constant. So that's it. So, not too shabby. All right. Now we have pendulums. So far, we could probably figure out the velocity of the pendulum, or we could figure out how high up it was if we did our energy LOL graphs. And also, it's like tracing out a circle. So you can do, like, remember how we were talking about in the circular motion thing, like when you're on a swing and how it feels different at the bottom of the swing than at the top? So, like, some centripetal force is involved, that kind of thing. So, a pendulum, you do need to know a couple things about a pendulum. So, usually the arm length is denoted as R, because it's like a radius. You may also see it as a capital L, which is length. And you can make it into a triangle with an X and Y component, and you can use sine and cosine to figure out, for example, how long the R or L is. So sometimes you'll need to do that. Yeah, triangles and sine and cosine. The length of the pendulum. So if I have this thing here, I could just measure the string, and that would be my R or L. Some of the really old AP questions will use L, and some will use R. Yeah. Because, yeah, sine is the Y component, and cosine is the X component. Yay! So, this is just a reminder that triangles are sometimes necessary to do things. And if you look at this animation here, you can kind of picture how circular motion is involved. Like, so remember, if I were swinging something like this around my head, it would have a velocity that's tangent to the curve. Like if this broke off, it would just fly off tangent to the circle. And the thing that's keeping it going in a circle is a centripetal acceleration that's pointing towards the center. So when it's at its lowest point, you'll see the acceleration points towards the center because it is kind of trying to do a circle like that. And the velocity is always going to be tangent to the circle there. Exciting? Okay, so ready for the equation for a pendulum? Here we go. Ta-da! So here's the equation, and you'll notice it looks very much like the one for the springs with just different variables. Y'all be nice. Oh, I heard the bus had an accident on the way to Florida.
Two buses hit each other.
Yeah, we were the bus that hit the other bus.
It wasn't a bad hit. It was just a bump.
Oh, okay. So it wasn't like a big deal.
They had to warn everyone about it. Yeah. They hit another bus. Just chill. No.
Oh, jeez.
I didn't know until somebody said something. So I thought a bump.
So wait, when was the band in Florida?
When was it?
Mm-hmm.
It was like the week of the egg drop.
Mm-hmm.
Like the day of egg drop. That's the day.
Okay, and when did y'all come back? Was it like Tuesday or something? So I guess I would have been in Florida at the same time. I got there on Monday. Anyway, so we got our equation here. So notice it's period again. So this is just a period of time measured in seconds. We have our 2 pi because we're doing a whole circle. And we have the length of the string over gravity. So on different planets, this pendulum would have a different period because we have different gravity. Crazy? Okay, so that's all I have for you for notes. That's literally the whole entire chapter. And now we're going to do a little lab.
Oh.
So let me just get that set up.